Yeah, good afternoon. Shall we? Okay, before we start, let's record this session. Mm, okay, so on Tuesday, okay, we discussed about first order system. Okay, um, we already see the behavior of first order system. Okay, the time response equation for first order equation is uh, 1 minus exponent negative t, basically. Okay, for the general equation. And you already see that in order to derive the equation, you do the step in uh, time response equation. Okay, or the ODE, Laplace transform, initial condition, input signal, partial fraction, okay, reminder theorem, and then you inverse the Laplace, so you will get the time response equation, right? And we also learn about classification, where we said by classify the system based on the order, okay, we'll be able to predict the behavior. All right, so we already discussed on first order system. Okay, so today we're going to continue with second order system. Okay, so again we start with the general transfer function for second order system. Okay, so second order system, of course, the highest order at the denominator will be to the power of 2. Okay, right, so that's determined this is a second order system. All right, and then in this general transfer function we have k. Okay, again k is the gain, similar to the first order system. K is a static gain, static transfer function. Right, we have omega n. Okay, and we also have zeta. Okay, so that is the parameter that we define the behavior of a second order system. Okay, so meaning the second order system, the behavior of second order system will very much depend on zeta, omega n, and k. Okay, so k is gain, zeta is damping ratio, and then we have omega n, which is the undamped natural frequency. And then later on, you also see another one is omega d, which is what we call as damped natural frequency. Okay, so this parameter k, we determine the response of second order system. Okay, and also is the design parameters. Okay, because later on you will see the value of, for example, if we discuss based on mass spring damper system. Okay, so the value that you choose for k, m, and c will meaning the k, zeta, and omega n will depend on the value that you choose for k. K here is the spring stiffness. Okay, there is different k: stiffness, mass, and damper. Okay, that's what we call as a design parameters, because we need to design the value. We need to choose the value for k, mass, and damper, damping coefficient. Okay, so based on k, m, and c, it will determine the value for the k, zeta, and omega n. Okay, so example of second order system, of course, any system that come that has a second differentiation term. Okay, d square y per dt square. Okay, if there is a term of the highest order of the differentiation term is d square, meaning that system will become very much will become second order system. Okay, what else? dy per dt, d square y per dt. Okay, so here we have m. Okay, that's why we have summation of force equal to md square md square x. Okay. All right. So that is the example for the second order. Okay. Next is, okay. So in order to get the time response equation, okay, this is the time response equation. Okay. We will do the same. The procedure is the same. Okay. Let's say, for example, here we have a spring mass damper. Then we're going to write the ODE. Okay, we produce the ODE of this system. Okay, and then we do all the steps. Okay, Laplace transform and etc. Okay, so after you inverse the partial fraction part there, okay, after you already determine A, B, and C, etc. Okay, you're going to inverse that, and then this is the general time response. Okay, meaning general here because we does not determine the value of zeta, omega n, alpha, and omega d. Okay, so that's why we call it in terms of general time response equation. Basically, it will produce the same form as this, okay, but it will the exact value will be depend on the value of zeta that we choose for your system, depend on the omega n. Okay. Okay. And alpha. Alright. Okay. Saya lupa nak tanya you all tadi. Mana soalan tadi? Okay, so your class haven't covered this part? This part?
Yes, not yet.
Not yet.
Yeah.
Alright. Okay. So okay. Okay. Let's go back to first order because you will not understand. It's not you won't understand. I should cover first order first before we can go to the second order. Okay. Sorry for that. Because yes, I have 3 sections, so I'm saya confused lah yang mana. So basically this is this morning session. So I already explained. So I think your section already covered this, right? Okay. All right. So we just stop until here, until classification.
Yeah.
Right. Thank you, Taufik. All right. So let's talk about first order system. Okay. So we have done classification, right? So I think I already mentioned that the most common classification that we use is based on order. Okay, so by knowing the order of the system, okay, we will be able to predict the behavior of the system. Okay, so after you have learned about first order and second order, okay, if you know the system is first order system, okay, you should know how it will behave. Okay, there is a characteristic that you can know about first order system and second order system. All right. So again, let's start for the first order. The general transfer function for the first order is k over 1 plus ts. Okay, so we have k here is static gain. Okay, where k will relate between it will relate between output and between output to the input at steady state region. Okay, we already discussed that time response, we have two parts. Okay, transient region, and then we have a steady state region. Okay, so k here is a static gain, so it will relate between the output to the input at steady state region, meaning we only consider at the steady state region. So the relationship is given by y is equal to ku. The output is equal to static gain multiplied with the input of the system. All right. That is the first parameter. The second parameter here is t. Okay. So t here, t is known as time constant. Okay. Time constant, the definition for the time constant is time taken to reach 63.2% of final value. Okay, so we can determine the final value based on this equation here. Final value will be the y at steady state. Okay, so time constant is the time, how much time taken to reach 63.2% of the final value. Okay, if the final value is 1, 63.2% is 0.632. Okay, time constant, time taken to reach 63.2% of final value. All right. Okay, so okay, the example of first order system is spring damper system. Okay, we already derived this system, spring damper system. Okay, and you will see that the highest order for the ODE will be first differentiation. Okay, we only have CD here, CD X naught. Okay, so that is the highest order, so it will become a first order system. Okay, basically we already derived for this. Okay, if you refer to the notes, okay, we already derived here, example 5. Okay. Okay. Second example of first order system is thermal system. Okay, so for the thermal system, the highest order is also for the capacitor, CD theta is equal to Qi minus Q naught. Okay, the second equation is resistance 1 over R. Q naught is equal to theta over RT. Okay, so the highest differentiation is d theta here. So this is also example of first order system. All right, so in this transfer function, okay, k over 1 plus ts, okay, So I call this as a general transfer function. Okay. It means that we have to make sure that every time we have a transfer function, we need to write in form of k over 1 plus ts. Okay, meaning 1 here must always there. Okay, for example, you have a transfer function y over u is equal to 10 over s plus 20. Okay, so you want to determine the what is the value of k and what is the value of t from this system. Okay, we know this is first order because this is s to the power of 1, first order, right? But in order to determine the value of k and t, we need to write the equation in form of general transfer function. Okay, so by saying general transfer function, the term 1 here must be there. Okay, so therefore we need to divide by 20. 20 divided by 20 will be 1. Okay, and then this is 20. This is divided by 20. So it will give you 0.5. Okay, divide by plus 1. 1 bagi 20 berapa? 0.1 bagi 20. 0.05 S. Betul tak? 0.05. Okay.
Betul.
Alright. Okay, thank you. Okay, so by rewrite the equation in form of general transfer function, okay, where we can see the term 1 here is visible there. Okay, so then we can compare. Say the numerator term is to the k, okay, and this one here as the t. Okay, so say by comparing like that, so we can say, okay, k is 0.5 and t is 0.05. Okay, so by knowing the value of k and t, we can predict the behavior of the system. Okay, when the most important parameter here between k and t, the most important parameter is t. Okay, for the first order, t is very important because we use t. Okay, t is used to explain how fast the output responds to the input. Okay, so t is an important parameter because t will explain how fast the system will respond after we apply the input. Okay, so basically T is used to explain the reaction, how fast is the response of the system, how fast is the behavior of the system after we apply the input. Okay, all right. Okay, so let's consider this transfer function again. Let's we have y over u is equal to k over 1 plus ts. Okay, and it said k is equal to 1. So let's consider 1 over 1 plus ts. Okay, let's just consider for k equal to 1. Okay, so ys will equal to 1 over 1 plus ts multiplied with us, because basically this is us, because the transfer function is already in Laplace s. All right, so it said that we apply with unit step input. Okay, unit step input. Okay, so therefore we have 1 over 1 plus ts multiplied with 1s. Okay, so we do the time response equation, the derivation of time response equation again. Okay, so we have 1/1 plus Ts multiplied with S is equal to A over S plus 1 B over 1 plus Ts. Okay, so if we do the remainder theorem, okay, A is equal to 1/1 plus Ts S multiplied with S, where we consider S equal to 0, okay, and for B, 1/1 plus Ts multiplied with S multiplied with 1 plus Ts, where we consider S equal to -1/t. Okay, so you can cancel this. This becomes 0, A equal to 1. Okay, as for this one, you can cancel this. B is -1/t. -1/t ke negative t? Negative t. -1/t ke t? Baca. Okay. So ys is equal to 1/s minus t or 1/t. Anyone can check for me?
Negative T.
Negative t. Okay. So it is negative t. Negative t. So it is equal to t over 1 plus Ts. Okay, so if we inverse that, we get 1, okay, minus t exponent negative refer table. Table kita. Table kita here. Salah. Okay, we have 1/1 plus apa tadi? Ts ke? 1 plus Ts kan? Okay, so we need to rewrite in form of S plus alpha. Okay, so S plus alpha, meaning this one we must be divided by t by t by t. Okay, so we get 1/t over S plus 1/t. Okay, therefore alpha is 1/t. Okay, therefore we get exponent negative alpha is 1/t. T kecil. Okay, T. Okay, so we have 1/t here. Okay, so by replacing there. Okay, so here after you inverse, you get.
Bukankah sepatutnya tadi T bukan 1?
Tadi 1, tapi sebab kita kena tulis dia dalam bentuk sama seperti dalam table. Dalam table untuk eksponen negatif alpha t, it is 1/s plus something. So kita kena tulis dalam bentuk yang sama. Okay, so here you get okay, you get 1/t exponent negative 1/t t time constant multiply with t. Okay, so this one is cancelled. So it become 1 negative exponent negative t per time constant. Okay, that is the general transfer function for time response equation. The general time response equation. Okay, because this is here yt. Okay. All right. So since this is the equation, right? Let's draw the. Okay, the equation is yt equal to 1 exponent negative t over t. Okay. Exponent negative. Okay. Right. So in order to plot the behavior, we're going to this is yt. This is t. Okay, so let's calculate for t equal to 0. T equal to t equal to 1, tak ada masalah, tak boleh. T equal to t. T equal to infinity. Dia t ke t per t? Ni. Sekejap. T per t ke t saja? Kalau t per t kosong. Just calculate ni je lah. Exponent negative t per t where we consider t equal to 0. Okay, of course you will get 0 here. Okay, if you replace t here with 0, okay, so you will get mana boleh replace t, apa term dia, 1 over t per t ke apa ni. Okay, 0, 1 t, 2 t. Okay, we're going to replace with salah bukan t ni. We're going to replace with 1t, 2t, 3t, 4t, and 5t. Okay, if like that, then only you can calculate. Okay. Okay. Okay, what will be the value for 0? 0 dapat tak?
0.
0 1t?
0.63.
2t?
0.86.
0.95?
Yeah.
0.98?
Yeah.
0.99.
Yes.
Because this is standard. Okay, so basically the value will be standard form. All right, so here we can see that when t here is t equal to t lah, 1t to t lah kan. Okay, where t is time constant. Okay, so it proves when time is equal to time constant, it will reach 0.632, which is 63.2% of 1, because this is unit step input. Okay, 1 here. All right, and then if we increase time by 2t, 3t, 4t, 5t, it will reach this value lah. Okay, so basically if you plot yt. Okay, so this is 0, 1t, 2t, 3t, 4t, 5t. Okay, so basically we reach 1. Okay, if you try infinity, you will get 1. Okay, so let's say 0.5, 0.6. So let's say here, okay, 0.632, 0.8, 0.95, 0.98, 0.99. Okay, so if we plot the behavior, we always be something like this. Okay, so this is the this is how first order response will look like. Okay, okay, it will have this kind of response. Okay, it will reach the final value. Okay, it will reach the final value. Because here we consider k is equal to 1. Okay, that's why it will reach the final value. Okay, and then this is time constant. Okay, where we said it will explain the behavior of the system in transient, meaning it will explain how fast the system will reach 63.2%. Okay. What else? Okay. So let's see. Okay, let's see the effect of time constant. Okay. Let's see the effect of time constant. Okay. Let's say we have a system. Let's say we have three systems, A, B, and C. Okay, we have three systems. Okay, the transfer function here is, this is the transfer function. Let's say the transfer function is 1 over s plus 1. Okay. 1 over 2s plus 1. And then 1 over 0.5s plus 1. Okay. Okay. Based on the transfer function, we can determine the value of k and t. Okay. What is the value of k for system A?
1.
Okay, 1. T? 1 plus
Also
S.
1.
1.
Also 1.
How about system B?
K is 1, T is 2.
Okay, correct. How about C?
K is 1, T is 0.5.
All right. Okay, so you just compare to the general transfer function K 1 plus TS. Okay, so 1 is there. Right, so we're just going to compare what is the constant value for S for the time constant, and then what is the value for the numerator for the K. All right. All right, so let's calculate. Okay, let's calculate Y final, which is, or sometimes we call it Y steady state. Okay, so I already said that Y is equal to, Y steady state is equal to K multiplied with U. Okay, we just consider at the steady state. Okay, so the input to the system is unit step input. Okay, We already derived just now. It is unit step input. Meaning it is equal to 1. Right? So by multiplying U with K, we get 1. Alright? Okay. Alright, because here we want to see the effect of time constant. We don't want to see the effect of K yet. Okay. For this system, we're going to study the effect of time constant. Right, so let's plot. Let's plot. Okay. Y. And we know all that we reach 1. Okay. All right, so system A, time constant is 1. Okay, so we know that the time constant will reach 0.63. Okay, because 63.2% of 1 is 0.63. So it all will reach this line here, 0.632. Okay, let me say this is 1, this is 2, this is 3. Okay. Okay, so A will reach here. This is A. Because it reached at 1 second. Okay. This is B, reaching 0.632 at 2 seconds. And then there is another one at 0.5. This is B. 0.5. System C will reach at 0.5 second. Okay. So now we can plot. Okay. So if we start from 0, 0 initial condition. Okay, it will reach. Okay, it will reach the. Okay, for A, I'm just sketching it. Okay. All right. So based on this plot here, we can see that system C is response faster compared to system A and system B. C is the fastest one. Okay, because we just compare the time constant. By knowing the time constant, the lowest time constant will give the fastest response system. Okay, so that is the effect of time constant. Okay, it will explain the behavior, how fast the system will respond to the input. Okay, so just by check the time constant here. Okay, boleh faham? Okay, alright. I think yes.
Yang Y final over Y steady state tu tak berapa nak faham.
We can sometimes we call it Y final because it's final value. Sometimes we also call it Y steady state, which is output at the steady state. Dia bukan Y final bagi Y steady state. It's OR.
Okay.
Okay. Alright, so now let's see the effect of K. The effect of K. Static gain. Alright, so let's do the same. Let's have a table there. A, B, C. Okay, we have transfer function. Okay, then let's determine the K and T. And then let's determine Y steady state. Okay, so in order to illustrate the effect of T, I'm going to choose you the same time constant. Okay, so here you will have 1 over S plus 1, 2 over S plus 1, and 0.5 over S plus 1. Okay, so by doing the same step, we will be able to determine the value of K and T. Okay, so by looking at, since this is already in standard form, general transfer function. Okay, so K is 1, this is 2, this is 0.5. Okay, as for the time constant, it's all 1 here. So this is 1, this is 1, this is 1. Okay, so by knowing the K, we'll be able to calculate the Y steady state or Y final. Okay, so the input is a unit step input 1. So 1 multiplied with 1, the final value will be 1. Okay, system B, 2 multiplied with 1, the final value will be 2. And system number 3 is 0.5. Okay, 0.5 multiplied with 1. Okay, U equal to 1. All right, so let's plot the system. All right, so this is time constant, T equal to 1 second. This is T, this is Y. Then let's say this is 1, this is 0.5, this is 2. All right. So based on the time constant, okay, system A will reach 0.632. Okay, so this is 0.632. This is for system A. For system B, the final value is 2. Okay, so 63.32%, 63.2% of 2 will be 1.26. 1.2. So half of the complex sini lah. .26. Okay, and for system C, this is B. For system C, the final value is 0.5. So 63.2% 0.05 is apa? 0.3 berapa? 0.25. Anyone calculate? 0.3
316.
Okay. All right, so system A, the final value will be 1. Okay, so the time constant is 1 second. It will reach 0.632, so it will behave something like this. Okay. For system B, the final value will be 2. Okay, and it reach 63.2% at of 2, which is 1.62. Okay, here. Okay, so you can get behavior. Okay, and for system C, okay, it will reach the final value 0.5. Okay, so it will reach something like this. Okay, so basically we can see here that the effect of K is just it will change the final value. Okay, we change the final value, and of course it will also change the time constant output, meaning the output at time constant. Okay, we have 1.26, we have 0.632, we have 3.16 because it depends on the final value, but it always 63.2% from the final value. Okay, so this is B, this is A, this is C. In terms of time, in terms of response, we can see its response. In terms of time here, it is the same. Okay, it will reach time constant at the same time. It will reach final value at the same time. Okay, but the final value will be different because the static gain is different. Okay, so that is the effect of K. Okay, so by saying that, okay, just now I give the general transfer function based on our derivation is 1 minus exponent negative 1 over t multiplied with t. Okay, but this one is we consider K equal to 1. Okay, K the static gain. Okay, but if we consider a general K, yt will equal to K multiplied with 1 exponent negative exponent 1 over t. Okay, this is the general time response equation by considering K and also time constant. All right, any question? Okay, so first order, you need to remember the general transfer function. Okay. Second, you need to know how to compare between your transfer function to the general transfer function. Okay. Make sure you always make sure it is in terms of 1 plus something at the denominator. Okay.
Doktor.
Yeah.
Yang Y steady state tu K multiply U kan?
K multiply U. Yes.
U tu dapat mana?
U is the input. Okay. U is the input where when we first derive, we use this system. Okay, the input is unit step input. Okay, and we consider K is 1. Okay, but if the input, but it is if it mentioned the step input equal to 2. Okay, meaning the unit is 2. So therefore, in Laplace, it is 2 over S, Laplace. But when you're going to apply K multiplied with U, so U is 2. Okay?
Faham.
Yeah? All right, let's go to the last example. All right, basically dah ada ni. Okay. All right. So example here, this is for the first order system. Okay, for the first order system. Okay, so the question asks you to find the transfer function of the motor. Okay, the system is a motor. Okay. The system is the motor, and then it asks you to find the transfer function of the motor, right? So the transfer function of the general transfer function will be torque equal to voltage, okay? Because the output is torque, the input is voltage, okay? So the output is torque, the output is voltage, is equal to K over 1 plus Ts. Okay, that is the general transfer function. Then we need to define what is K and what is T. Okay. All right, the information given is a time response test with a 6 volt input voltage. Okay, so U is equal to 6. Okay, it's like the input is 0 volt, then you suddenly change to 6 volt. Okay, so it is step input. Okay, so before it start it is 0, then you change to 6 volt. Right, so It is step input because it stay at 6. Okay. So it is step input. The unit is 6. Right. We're going to use that in order to calculate K or Y final lah. Okay. That is the first information. The second information is resulting in steady state torque, output torque of 20 Newton centimeter. Okay. So meaning we can write torque at steady state is equal to 20 Newton centimeter. Okay, so you apply 6 volt. Okay, the system will slowly respond to it, and then finally it will produce 20 Newton centimeter. Okay, because it's first order, so it will take some time. Not directly you apply the input and straight away get 20 Newton per centimeter. Okay, because we know this is first order, it will have some delay there. Okay. All right, so therefore here we can calculate for K because we know K is equal to Y steady state divided by U. Okay, so our Y steady state is actually the torque steady state. So 20 divided by 6 will give you 3.33 Newton centimeter per volt. Okay, so this is our K. Okay. So now we need to determine for T. Okay, we already have K. Now let's determine for T. Right, so the information here is it took 0.4 seconds to reach 12.6 Newton centimeter. Okay, meaning there is some delay. So in order to reach 0.6 Newton centimeter, it will take 0.4 seconds. Okay. So we know the final value is 20 Newton centimeter. Okay, and then if you calculate 12.6 is actually 63.2% from 20. Okay, multiply 63.2% from 20, it gives you 12.6. All right, so meaning 0.4 here is our time constant. Okay, so therefore the transfer function will become 3.33 divided by 1 plus 0.4 S. Okay, so that is for example number 1 for the first order system. Okay, so basically ada example lain, second order next week lah. Okay, so any question for the first order? Okay.
Doktor, boleh ulang balik tak cara dapat T tadi?
Cara dapat T?
Ya.
Okay. Cara dapat T cara dapat okay, based on this statement here, it took 0.4 seconds to reach 12.6 Newton. Right? So Y final or Y steady state is equal to 20. 20. Right? So if you divide 12.6 over 20, this will give you 63.2%. Kalau you dah persen lah. 63.2% lah. 0.632. Okay. Okay. So by knowing the information that the time constant is the time taken to reach 63.2% of the final value, which is in this case is 12.6. Okay. So it's already given to you that the system reached 63.2%, which is 12.6, is 0.4 second. Okay, so meaning 0.4 second is our time constant. Okay.
Okay, faham doktor.
But because in this example, it gives you straight away, it gives you the answer. But if the time, meaning let's say it mentioned here is took okay, if it give you, it took 0.4 second to reach, let's say it's not 12.6, but 10 Newton per centimeter. Let's say this is the kind of information given to you. Okay, so in order to solve this, you're going to use the equation yt k multiplied with 1 minus exponent negative 1 over t. Okay, so now you know k is already known. Okay, so from the equation 0.10 Newton per centimeter is equal to 3.33 multiplied with 1 negative exponent negative 1 over t. T is the one that we want to find, where the time is 0.4. Okay, so you need to solve this equation to get time constant. All right, so we're going to use the equation, the time response equation. Okay?
Okay, understand doktor.
All right, so I think we stop here. It's 1 o'clock already. So, okay, Assalamualaikum warahmatullahi wabarakatuh.
Thank you doktor.
Thank you, doktor.
Thank you, doktor.
Thank you, doktor.
Thank you, doktor.
All right, selamat.
Thank you, doktor.